Okay, so in this section we're gonna take a look at a surface area of a solid of revolution. All right, now in a previous section in Math 1 in the first semester, we've tried to find the volume of a solid of revolution, right? So we had some curve right on the XY plane, as you can see here, right? The XY plane noted on the grid part here. And then we rotate it about a given axis. Here, we're going to rotate across the x-axis. And we come up with some solid. All right? And we were able to calculate the volume, right? In other words, how much capacity does it have, right? If we were to fill it with some kind of liquid, how much liquid will fit in there. So in this section, we're going to take a look at a different problem. We're going to take a look at the surface area. Right, so I'm not interested in how much to fill it, but let's say I wanted to paint it, right, around on the outside. All right, how much area, right? So previous volume cubic units, here area, right, space, right, covered, it's square units. Okay, now let's try to figure out what the process like that would be, all right? Now if we think of a curve here, in the XY plane. So we have some kind of curve. And we're going to rotate this across the x-axis. So we have some kind of rotation here. Right, and I want to calculate the surface area. All right. So again, I'm going to do what I always do with these types of problems, right? What we've done before is we think of approximating a smaller section of it. All right, now before we get to that, let's take a look at, how we calculate the surface area of some three-dimensional object, right? So let's say we had just a cylinder, right? So we'll look at something like a cylinder of some given radius and some given height, right? Imagine like if you had a sheet of paper and you rolled it up into a cylinder. All right, now think of if you take some scissors and you kind of cut along that cylinder here, and then if you kind of lay it flat now, right? So now you see the area that it covers. It would have this rectangular shape. All right. Now, one of the sides would be h, all right? Now this other side, right, h the height, this other side here, if you look at how we created this rectangle, well, it would be this circumference of the cylinder. Right here, the circumference being 2 pi r, right? So the other length of the rectangle is 2 pi r. Right, so now the surface area for a cylinder would just be 2 pi the radius times h, right? So surface area 2 pi r h, right? Length times width. That's for a cylinder. Now, here, we're not going to really be dealing with cylinders unless we have just a straight horizontal line, right? What we're going to be dealing with, if you kind of can imagine here, it's not quite a pyramid, but it looks like a pyramid with part of the top cut off, right? Sometimes called a frustum, right? Where you think of a pyramid, but you just kind of chop off the top part of it. Now, how would I find the surface area of something like that? Well, let's take a look first at what if I did have some pyramid here. Pyramid shape, or cone shape, I should say, not a pyramid, right? Some kind of cone shape, right? Where I'll call this lateral length L, and it's of some radius R. Right, and I do the same thing that I had with the cylinder. Well, I'll cut across here, and then I'll lay it flat. Now, in this case, I don't get a rectangle, but I get some sector of a circle, right? Where this quantity here is some angle theta, right? Now, this arc length here, this length here, right, can be calculated by 2 pi r, right? The circumference of our circular base of our cone here. Right, and then here the lateral length we said was just L. All right, now I have a formula for the area of a sector of a circle. Right, that formula, right, is going to be, which maybe you learn in a trig class, a geometry class. If not, we can easily just look it up. It's 1/2 L squared theta, right? Where I hear it's important theta in radians, right? Because it's a unitless quantity, right? If we had degrees, then we had to make some kind of conversion. Our units wouldn't be unit squared. It'd be unit squared degrees, right? Which is not helpful, right? Hence the use of radians, right? Which is why it's preferable, especially in applications, to use radians because of its lack of units. All right. Now, the quantity theta in my calculations, I really don't need. I don't want it. Right? I don't really want the theta. I want it to be in terms of L and R, if possible. Right? In particular, just so what I'll do is, if we recall the way radians are defined, right? Radians are defined as the ratio between the length of the arc being swept out and the radius of the circle. In this case here, it's tricky because I'm talking about two different radii, right? By the radius of the circle being swept out here, I'm talking about L, right? So theta is actually defined, can be defined as 2 pi r over L. Right, radius of that angle being of what's being swept out over the length of the radius of the circle that we've defined. Okay, so now I can simplify my area formula to be 1/2 L squared, and then theta is 2 pi r over L, which just reduces to pi r L. Okay, nice. So in terms of R and L, right? I don't have to worry about any kind of angle. Okay, so now let's, we still haven't gotten to trying to solve this particular problem that we wanted to solve, right? So we'll get there. All right, so now the next step is, well, let me develop a formula for the area of a figure like this little cone with the top cut off here. So here, just kind of bear with me here as so we imagine a cone here. Where the top has been cut off. All right, so really the dotted line represents the phantom part of the cone, right? That part's not really there. What I want to find is how can I calculate the surface area of something like this, right? Now, not quite this, right? This is not the formula, although I am going to use it to calculate this part right here, right? So the way I can think of the surface area is I can think of two cones here, right? The smaller one here, where we have, I'll call this R1, and I'll call this part L1, right? This will just be from here to here, right? And I'll call this quantity L, from here to here. Okay, so I can think of the area of just the frustum here to be the area, the surface area of the larger cone, which I know to be pi, the radius, I'll call this radius R2, pi R2, and then L1 plus L. Minus, right, because that's too much, right? I don't want all of it, I just want this piece here. Minus the surface area of this smaller cone, and that's just pi R1L, right? Okay, again, I'm just using the formula that I have defined up here, right, for the smaller cone and then the overall larger cone here. All right, so far so good here. I'm going to factor out. They have a common factor of pi. I'm going to group some like terms here, and we'll see why I want to set it up in a second here. So pi, right, I'm going to take a factor out the pi, and I'm going to group the R2s, or the L1, excuse me, and the L. So we'll have R2 minus R1 times, oh, excuse me, this is R1 L1 times L1, and then plus R2L. Okay, so here what happened, here I distributed R2, and then I grouped L1 is R2 minus R1, and then R2L. So what's left here, and then the pi I factored out of both here. Okay. Okay, now. So now let's look at what we're going to do from here, right? So I'm going to do a little simplification by using some similar triangles here. So if we think of this as a kind of, instead of a three-dimensional object, we can look almost like we flatten it out. And we have this quantity R1, this quantity L1, and again, this is quantity L, but just from here to here, and this is R2. And by similar triangles, we have L1 over R1 to be L1 plus L over R2. So here, let me, and then doing a little cross multiplication, we get R2 L1 equals to R1 L1 plus R1 L. And again, now rearranging, well, I'll bring the quantities with L1 to one side. We get R2 minus R1 times L1 is equal to R1L. Okay. All right. And now notice here, what we see here is we see this quantity here shows up here. All right. Now, what that allows me to do is eliminate that L1, because again, that's not a part of the surface head that we're looking for, right? I want it in terms of L. Okay, so now let's do that substitution. All right, now substituting back to our area formula, we get area is equal to pi R1L plus R2L. Factoring out the L, we get pi L R1 plus R2. Okay. All right, and again, I'm going to redefine this R1 and R2 as just a general R, but I'm going to define R to be the average of the two, right? And we'll see in a second why I want to do that. And taking those intervals, we're going to do the same thing. We're going to set up some kind of Riemann sum. Taking those intervals, we'll see that we squeeze those intervals smaller and smaller, so we can just have R to be one and the same as R1 or R2. Now, to account to that factor of 2, right there, I'm dividing by 2, so I don't have that here. So my formula would actually simplify to A equals to 2 pi RL. All right, so when I substitute that in, the 2's cancel, and I'm back to my formula from above. All right, so now how do I use this to find the surface area, right? Now, one thing to keep in mind is, from the previous section, the arc length, that L is the arc length, right? L is, excuse me here, L is this quantity here, right? L, and then our R1 and R2 are these quantities here. Okay, which is nice because I already have a formula for the arc length. Right, so now that's going to tie into the surface area. All right, so now let's go back here and solve that surface area problem. All right. Okay, so again, we focus in on a partition of our interval, right? So we have here, and we take a look at just a general partition. We'll call this x sub I minus 1, and then x sub I. All right, and we focus on the rotation of this quantity across the x-axis. Okay. So if I think of that as just one section of my overall curve that I'm after the surface area, then I can go ahead and use my formula to calculate the surface area, which I'll denote as S, as sub I, right? That'll be 2 pi R L. Okay, now we already said that L was this, right? And R, we'll call this R sub I minus 1, and this one R sub I. Right, and R is just, we'll actually call it R sub I star and L sub I. Right, L sub I. Okay, and R is just, I choose one inside the interval here, right? And I choose it in a particular manner, right? I choose it where the derivative is equal to the average rate of change, right? And we'll see that we make the interval smaller and smaller, so the choice of it really doesn't matter, but we choose it in such a way so that it is the derivative of that is equal to the average rate of change, which I know exists because of the mean value theorem. All right, now plugging this into our formula here, we have 2 pi, right? It's just a constant. This R sub I is just the value of the function, right? And this L sub I is the arc length. So square root of 1 plus f prime x sub I star squared dx. Oh, not dx yet, still delta x. All right, so now that's just one of these little frustrums, right? Just an approximation, right? I can add all of these up across the interval to still have an approximation, but to make find an exact value, to find the surface area, we take the limit as n goes to infinity of the sum from I equals 1 to infinity here of 2 pi f of x sub I star square root of 1 plus f prime of x sub I star delta x. All right, and again, as long as certain conditions are satisfied, in this case, well, that the function itself is continuous, then this will converge to the definite integral across the interval AB of 2 pi f of x 1 plus f prime of x quantity squared dx. All right, and again, all this is with rotation across the x-axis. Now, if we're rotating across the x-axis and the function is defined in a manner that's easier to do the other way or more, and so again, we'll define this C and D. Right, so here where it's better if x is g of y, right? In other words, it leads itself to a simpler calculation. Then the surface area formula is the integral from C d 2 pi, and then it's y, right? Still f of x, right? Remember, y is equal to f of x, right? Still y, and then square root of 1 plus g prime of y squared dy. Right? Now for shorthand, this quantity here is the arc length, usually in text denoted by ds, lowercase s. Right? So in general, our formula for surface area is, along the x-axis, is 2 pi y ds. All right. And depending on what we want to use, if we want to use dx, then we just substitute the value for y. If we use dy, then we leave the y as is. All right, so this is rotation about the x. For rotation about the y-axis, right, then we will use 2 pi x ds. All right, where ds would take on the form of same as above, right? If we have here, either it's this one or this one, right? Depending on what function is easier to evaluate, right? So it'll be ds would be either square root of 1 plus, right, f prime of x squared, or dx in this case, and then you leave the x alone as is, or 1 plus g prime of y dy. Or in this case, x would be a function of y. Okay, so we would have to replace that, right? Because if it's a dx, all variables need to be x. If it's a dy, all variables need to be y. Okay, let's work through an example here. So find the surface area of the function y equals to root 4 minus x squared rotated about the x-axis between -1 and 1. Okay, so what we have here, this particular function is the top half of the circle above the x-axis of radius 2. So the function itself looks something like this. And I'm interested in the portion between -1, and 1. So I want to rotate this across the x-axis, right? So some portion of the sphere. All right, if I were to rotate this whole thing, we'd get a sphere. But I'm looking for this kind of band of it, right? Think of a sphere with the top and the bottom parts cut off. All right, and we're left with this figure here. So I want to determine the, excuse me, I want to determine the surface area. All right, so consulting my formula, we get 2 pi y ds, right, for rotation across the x-axis. All right, I think here it's already solved in terms of y, right? So I'll use this to be my f of x, right? In this case, y equals f of x, which in this case is root 4 minus x squared. Okay, so my formula is going to come down to evaluating the following integral, right? The integral from -1 to 1 2 pi f of x square root of 1 minus f prime of x squared dx. All right. Okay, so now let's plug things in, right? First, we need a derivative. So let me find the derivative of f. F prime of x is 1 over 2 root 4 minus x squared. Chain rule, -2x. So that leaves me with -x over root 4 minus x squared. Okay, and then I have f of x. So now let's plug things in, right? So here we have the integral from -1 to 1, 2 pi square root of 4 minus x squared times the square root of 1 plus -x over root 4 minus x squared dx. All right, and now here, it looks really messy right now, but let's simplify, right? Simplify, see what this looks like. Again, -1 to 1, 2 pi. Now, one thing I am going to do here is, these are both roots, so I'm going to write it as one big root, but I do have to be careful how I do that. This quantity is one term, so it's 4 minus x squared, and then this quantity is another term, so leave it like this. When I square this, I get -x squared is just x squared, and then down here, the root square it leaves me just with 4 minus x squared. All right, be very careful in how you do this, right? Now I'm going to distribute here, right? Remember, this 4 minus x squared is one term, so I'm going to distribute in here. All right, now again, still looks really intense, but we're going to see here in a second. This actually is going to be really easy here. So 4 minus x squared times 1 is 4 minus x squared. Now distribute to the other term, x squared over 4 minus x squared. Notice that these terms are the same. One's in the numerator, one's in the denominator, so they reduce to 1, and I'm left with simply the numerator of x squared dx. All right. And now we have here the x squareds cancel out, and we're simply left with root 4, but that's just 2. There's already a factor of 2 out there. So we get 4 pi dx. And now we get 4 pi 4 pi constant, so I'm integrating 1 essentially, so that is x, evaluated at 1 and -1. So that's 4 pi 1 minus -1, 2. There's already a 4 out there. 8 pi. 8 pi units squared. So that is my formula. Okay, now this one, the surface area is a bit more involved at the arc length, but for now, the same idea, right? Identify which formula you're going to use here. There's more choices here, but once you've identified it, then it's really just a matter of plugging them in and seeing if we can do the integral. Okay? All right.